Hi, welcome to a lecture which is about Introduction to Statistics in Julia. We are learning these basic fundamentals which are ultimately required for implementing machine learning in Julia. So this would be the last lecture which is about the techniques within data science, and in this particular lecture we'll be focusing primarily on statistics. The content of the lecture is very simple, but it's more about getting familiarity with how you implement this in Julia. So what you can do is you can probably code along with me by opening a Julia notebook in the Jupyter lab. So let's start. So in statistics, the main two things that we talk about is tendency for data to be centered around something and tendency for data to be away from that center. We might measure this using mean, the tendency to be centered using mean, mode, median, etc., and tendency to be away using range, standard deviation, variance, etc. So there are different mathematical parameters that we can describe, and today we'll be implementing some of them on some simple dummy data set to familiarize you with this whole thing. So mean, as you know, it's simply the average of the data set. So if you have 10 numbers, mean is the sum of those numbers divided by 10. Median is when you sort the data in ascending order or descending order, whatever comes in the middle. And if you have even number of data points, then there is no center, right? Then there are two values which are there in the center, then you can simply take the average of those two and describe that as the median. And mode is the most commonly occurring value in a set of numbers. So here I have written the code snippet which we will be writing in Julia as well. But basically just look at the packages that are used. Statistics package is being used, DataFrames for defining this data frame. With this we have already seen in some of the earlier lectures. And here we are defining the data set. You can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers and mean is simply sum of these divided by 10. Mode, I think we can see that 14 is occurring 1, 2, 3 times. So I guess 4 and 12 is also occurring 3 times actually. So there are two modes, 12 and 14. And median, I have to kind of arrange this in the ascending order or descending order, but I guess the median would be 14, I guess, because there are 3 values that are 12 and 3 values that are 14, and all other values are greater than 14. So I guess 14 would come in the middle. Anyway, so we'll first define the data, and then we will compute mean, median and mode. So here what I want you to focus on is, for mean there is already defined function. Simply use this mean. You can get that if you import the statistics package, and it's simply data.values, because in data frame you are defining a values kind of column in which there are all these numbers. So data.values means you will be fetching all these numbers, and mean of that means you are calculating the mean of all of that. So we'll write this code. I just want to show you the code first before writing it ourselves. And then median also is used calculated using this function. Mode is calculated differently. We are defining a function called mode here, and we will be doing this from scratch. So let's first open the Jupyter Lab notebook. So go to terminal. If you are on Mac, if you are on Windows, go to command line interface, and here I don't have a Jupyter notebook open. I'll just zoom in this a little bit and write Jupyter notebook. So obviously needless to mention, you should have Jupyter notebook installed. You should have Julia for Jupyter notebook installed, as well as you should have Julia itself installed. So assuming you have done those things from the previous lectures, if not, just go to the first lecture in this playlist. It's fairly easy, should not take you more than 5 minutes. Click open Jupyter Lab here. So Jupyter Lab will open a fresh notebook here, and these are some of the notebooks which we have been working on in the previous lectures. So I'm going to close this, and we can start from a fresh notebook, new Julia file. Oh, actually I want like a notebook, so I'll click Julia 1.1.1 notebook, and it's not IPy notebook, so right click, rename. This could be statistics in Julia. I'm just titling the notebook like this. And now let's import the two packages, right, using statistics and in the same code block I can write using data frames. Then let's run this, and once this is done we can define a data frame. So data equal to data frame of values equal to I guess I need to check the syntax here. Yeah, it's correct only, values, and we can define some certain numbers, let's say 3, 22, 12. I'm going to write some random numbers here. Okay, so we have a certain set of numbers, and now what we can do is mean value. We can define a variable called mean value equal to, okay, firstly they are printing the numbers, so these are the set of numbers, right, and the mean value is mean of data. It's not simply data, right, because it's a data frame, so we have to get the variable inside that. So it's data dot values, that's the value of the column, and the mean value is 20.833. I think we can also try to print just print data dot values to see the length, 12 element vector, right, so that we have 12 numbers here, that's why it's a 12 element vector. Anyways, so this is the mean, and we can now calculate. Let me put a like a markdown title here saying mean value. This is fairly straightforward, so I'm moving a little bit fast here because I don't want you to spend so much time on basic elementary concepts, but still I want you to get a hang of this, right? So if you feel like I'm going a little bit fast, that's because I don't want to spend too much time on this. We want to move into advanced concepts soon. So mean value is this, then median value equal to median of data dot values. And so the reason why here median is a number which is not present in this list of numbers is because it's there are 12 numbers here, which means it's an even, the length of this set of numbers is even. So there is no clear midpoint. There will be two numbers which are there in the middle if you arrange this in the ascending order or descending order, and this 8.5 is basically the average of those two. But if we delete, let's say if we delete this 51, then median would be one of the numbers from this list after rearranging. So after rearranging, I would say probably there are now 11 numbers, which means the sixth number should be the median. So 1, 2, 3, 4, 5. So probably 12 should be the median, I guess. Let's run. Oh, it's 5 because yeah, there are 1, 2, 3, 4, 5. Yeah, okay. 5 is the sixth number. So 5 is the median, and mean value should also change now because we have deleted one number, right? So this is the mean and median. Now let's come to mode. Mode is a little bit more tricky because if you try to do this, I believe it should not work. So mode is not defined. We can also search, right, like function for calculating mode in Julia. I'm not sure if there is a function like that. Okay, there is a stats based package using which I guess we can. This will cause an error, but eventually, yeah, I'm not sure if. Okay, let's try this. I'm not sure if this package is relevant right now. Let's see. So using stat base, yeah. So this is not import. Okay, I have to install it. So import pkg.add stats base, and using stats base. So this should install the package, which I have never used, right? So that's the reason why we had to run this import package. You don't have to run this all the time. You just need to run it once to install the package. Once it's installed, you can simply use the using stats base. So you can run it here, or you can run it in the terminal after opening. So you can go to terminal and you can open Julia like this. So this should open Julia REPL, REPL, and here also you can write import import pkg, and then pkg dot add stats base. You can type here. I'm not going to do it here because anyway this it's being executed here. So I'll close this terminal. So this is now installed. So I can remove this, and then perhaps mode of data dot values. I don't know if this works. Okay, it's working. So there is a mode function within the stats base package. What I had written previously was a function because this within statistics a mode function was not existing. So here what we did is we defined like a variable for calculating the count of numbers. So let me do one thing. Let me just copy paste this, and I just want to show you the execution of this function. Although it won't be very useful for you, it's not needed. You can simply call the mode function from this stats based. So let's compute the mode. Maybe I can change this name because it might be there is a mode function defined in the stats base. So if I use mode here, that won't be good. So mode function, and then I'm calling mode function here. How about this? Okay, so basically this function also calculates the mode, and let's see what's happening here. So mode function is being called, and into that data.values is being passed, and that is here in the variable called x. Now imagine that we were running this counts equal to count map of x. What should happen here? So counts equal to count map of data.values. What should this print? So then let's see. So here this count map function is very interesting because it maps every number in the list or in the array to the number of times it's occurring. So 5 is occurring only once in this. 1 is occurring only once, but 3 is occurring 4 times, and rest of the numbers are also occurring only once, which means here you can see that 5 is mapped to 1, 22 is mapped to 1, but if you look at 3, it is mapped to 4, right? So that is what this the count map function does. And then the max value, what here we are doing is maximum of values of counts. So basically this is like a dictionary key to value mapping, right? So here if we run something like max of maximum of counts. Maximum of counts is not valid because you have key value pairs. Okay, I guess you are just looking at the maximum value in the key. 61 is occurring once, but if you want the value within the key value pair, so this is key and this is value. So we are looking at the values of the key value pair in the variable called counts, and then you will get 4. Why? Because let me print. So when we print counts, you can see that among the key value pairs, the maximum value is 4. This is the maximum value, but maximum key is 61. So that's the reason why if we just put counts, it will print 61. 61 mapped to 1 because 61 is the biggest key and it's being mapped to 1, but we want the biggest value. And then here what we are doing is in the key value pair, return key if value equal to maximum value. So basically let's not return, let's just print here. So we can print key for key in value in counts. So basically counts is the dictionary. So in counts, if value equal to max value, so max value is how much? 4, and actually here we have to define max value. I'm just rewriting the function to take you through it in a bit more easy to understand way. Maximum of value of counts. So now the max value will be 4, and now it will iterate through all the values, and then it should print whatever is the key corresponding to that, and key corresponding to 4 is 3. So now if we run this, value is not defined. in main, because let's see what's okay. There is just a typo here. This should be values, and then here I can simply put value. Okay, so it's a one element vector. So basically what we are doing here is max value is 4, and here it's iterating through all the key value pairs, and if value is matching with the max value, we are outputting the corresponding key, and the corresponding key is 3, and which is same as the mode which you have from the mode function from the stats base, right? So this is mean, median and mode calculation in Julia. In my opinion, mode is very rarely used. I have, in fact, in none of the actual projects that I have worked on, I have never used mode. Mean is the only thing which I have actually used most frequently, but nevertheless it's good to see the logical implementation of mode without using the inbuilt function. Now the other two concepts are variance and standard deviation. Any data set, to describe that data set statistically with just two numbers, one of the numbers that you use is mean value, second number that you use is the standard deviation, or how much the data has spread across the mean. So variance measures the spread of the data. In simple terms, it's something like this. So let's say you have a data set which is x1, x2, etc. up to xn, and let's say mu is the mean of these data sets. Then variance is nothing but x1 minus mu the whole square plus x2 minus mu the whole square plus etc. up to xn minus mu the whole square divided by n. This is the variance. You can also write this as sigma I equal to 1 to n xi minus mu the whole square divided by n. So you can describe it like this, and standard deviation is nothing but square root of this. So square root of variance is standard deviation. So here again we don't have to define any functions. The function var, it's the variance, and it's already defined since we are using the statistics package, and standard deviation is simply std function. Otherwise we can simply take the square root of variance. So let's calculate this also. So let's go back to the notebook, and I will, for the sake of completeness, I will put a markdown here, variance and standard deviation, and we have standard deviation of data equal to variance first, variance of data equal to var of data dot values. So this is showing the variance, and obviously it's a big number because the order of magnitude of variance will be because it's a square of numbers, right? So usually you will see that standard deviation, if the data set looks like this, standard deviation also will be like a fraction of the general trend of the data, let's say 1/10 of this or something like that. But here suddenly you have a huge value, 463. It's nowhere the present, it's not even within this general set of numbers here in the data. That's because the squaring factor is coming. But if it's standard deviation, then there is no problem, because std of data equal to std of data dot values, see 21.5. So that is now in the general set of, it's kind of, it makes sense that this data can have a standard deviation of 21.5, because the minimum number is 1, maximum number is 61. So it has a good spread. So this is variance and standard deviation, fairly easy. We don't have to use any we don't have to define any custom function. These are all already inbuilt functions. So that is variance and standard deviation. Now there are a couple of things which you will 100% encounter while working on actual data science related projects. One is correlation and another one is covariance. So correlation and covariance are basically something that measures the relationship between two set of data sets. So here we are defining a data frame with one set of data called X and another one called Y, right? So here is X, here is Y, and here we are calculating the covariance and correlation. And covariance and correlation between what? Between data 2.x and data 2.y. So what is data 2? Data 2 is this variable in which this whole data frame is stored, and data 2.x means this entire set of numbers. Data 2.y is this entire set of numbers, and here we are calculating the covariance and correlation. And I just want to first show you this with an actual data set and actual code. So let me write the markdown: covariance and correlation. And we can define data 2 equal to data frame of x equal to 1, 2, 3, 4, 5 and y equal to 6, 7, 8, 9, 10. Okay, so data set is defined. Now covariance equal to COV of data 2.x comma data 2.y. So covariance is 2.5, and actually if you only define this, covariance of data 2.x is 2.5. What about data 2.x comma data 2.x? Okay, now it's very high. So we can just have a look at the covariance formula just to get an idea. So basically this is how it is defined. So covariance is xi minus x bar, which is the mean of all the x values, and yi minus y bar, which is the mean of all y values. So in our particular case, the data set that we had used was 1, 2, 3, 4, 5. The mean of this is 3 and the mean of this is 8. So now if we were to calculate the covariance, we have 1, 2, 3, 4, 5. This is the first data set. 6, 7, 8, 9, 10. And x bar equal to 3, y bar. So this is the data set x, and this is the data set y. Y bar equal to 8, and x minus x bar times y minus y bar, yi minus y bar, divided by n minus 1, and you go from sigma n I equal to 1 to n, because you have n equal to 5 here. So you are going from sigma I equal to 1 to n. Now let's go back to the Miro board. So we can, I think we can relatively easily calculate this, because 1 minus 3 is minus 2. Here also it's the same, so it's minus 2 times minus 2, 4. So the first set of multiples will be 4, plus minus 1 times minus 1 is 1, plus 0, plus 1 plus 4, divided by 5 minus 1, this is 4. So this will be 4 plus 4, 8. 8 plus 2, 10. 10 divided by 4 equal to 5 by 2 equal to 2.5. So this is the covariance. Now if we were to calculate the covariance between this 1, 2, 3, 4, 5 and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 and 1, 2, 3, 4, 5. Then that will also be the same, because here you see it does not matter whether the mean value is higher or not. Here we are looking at the covariance, right? And you can understand this covariance visualized. You can understand this when you look at this plot basically. So I could not find a really good visualization that shows covariance in a bit more intuitive manner, but we can explain it in a relatively easy way, right? So imagine that you have two companies and their stock prices. Let's say the stock price of company A is something like this, and then stock price of company B is something like this. Then here you can see that whenever stock price of company A is increasing, then company B's price is also increasing, and vice versa. On the other hand, if you had a company whose stock price, let's say it looked something like this, something like a mirror image of this, then it means that whenever the stock price of the first company is increasing, the other one is decreasing. Like, oh, sorry, let me just draw it. We can take a mirror image of this. Okay, not exactly this, but we need to flip it. Something like this, for example. So here, whenever this is rising, this is decreasing. Whenever this is rising, this is decreasing. So these two have positive covariance, because when one is increasing, the other one is also increasing. These two have negative. So that's the reason why here, if you have a set of numbers like 1, 2, 3, 4, 5, and another set of numbers like 6, 7, 8, 9, 10, and another set of numbers like 11, 12, 13, 14 and 15, there will be positive covariance between this and this. There will be positive covariance between this and this, and it will be exactly similar, because whenever this is increasing by 1, these set of numbers are also increasing by 1. These set of numbers are also increasing by 1. But now imagine you had another set of numbers like 20, 19, 18, 17 and 16, right? So now if you look at this set of numbers and this set of numbers, whenever the number in this set is increasing from 1 to 2, 2 to 3, 3 to 4, this is actually decreasing. So now let's go back to the covariance formula. It is xi minus x bar, the whole multiplied by and yi minus y bar divided by n minus 1. So now this will be xi minus x bar is minus 2 for this, because this is 1 and mean is 3. So minus 2 times yi minus y bar is 20 minus 18, because mean is here is 18 times 2. So this is minus 4 plus minus 1 times 1 plus 0 plus, I am doing the calculation with respect to this formula, so please bear with me when I am moving fast. Then you have xi minus x bar is 1 for this, but minus 1 for this, so it will be 1 times minus 1 plus 2 times minus 2 divided by n minus 1 is 4. So this will be minus 4 minus 1 minus 1 minus 2 minus 4. So that will be minus 10 divided by 4 equal to minus 2.5. So see, the value is exactly the same. Here also it was 2.5. Here also it is, the magnitude is 2.5, but the sign is negative, because every time this is increasing by 1, this is decreasing by 1. So there is negative covariance between these two. So that is the intuition behind covariance, and you can calculate it using this function. So here let me run this once again. Here it should be 2.5, and we had one more parameter called correlation. So correlation equal to data2.x cor, and correlation here in this case is 1. And how do we calculate that? Let's open the formula, correlation formula. So here just look at the formula. The numerator is pretty much same as covariance, right? So it is sigma xi minus x bar times yi minus y bar. But in the denominator you have a square root of sigma xi minus x bar the whole square, sigma yi minus y bar the whole square. This value is a positive number. So let's write the formula here. Actually, before writing the formula, let's try to get a logical understanding here, right? So instead of 6, 7, 8, 9, 10, let me write this as 10, 9, 8, 7, 6. So now here covariance will become Oh, here I have written x only, so let me convert this to y. Yeah, covariance will become minus 2.5 and correlation should be actually, oh, I put y, instead of y I had put x earlier, so correlation is minus 1 here, and if this was in the other order, correlation will be 1, 7, 8, 9, 10. So basically correlation is nothing but covariance scaled by another factor. So the sign of covariance and correlation has to be the same, because if you look at the formula for correlation, the denominator is positive, numerator is this, right, sigma xi minus x bar times yi minus y bar. Covariance formula also has the same numerator, sigma xi minus x bar yi minus y bar. So the sign should be the same, but here the denominator is simply n minus 1, here the denominator is sigma xi minus x bar times sigma yi minus y bar square, xi minus x bar square and sigma yi minus y bar square. So essentially they will give you similar type of information, but with a different type of scaling. So that is covariance and correlation. I'm 100% sure that you are going to use this at some point in your machine learning journey. So be very familiar with this concept of correlation and covariance. You have to be able to define this to sometimes know what are the features in a certain data set that influences the model prediction. So for example, there is a famous Titanic notebook. It's like about predicting the survival probability of passengers on the Titanic, and there some features are positively correlated with survival and some features are not so. And there are many other data sets where if a particular value gets higher, then the chances of being predicted as one class will be higher, whereas if there are some other features where high value of the feature will mean that the prediction class will be flipped. So defining the correlation between certain features in the data set and the predicted label, or the actual label, will help you identify the features of more relevance, and that will help you do proper feature selection in machine learning. We'll be of course covering all of that in detail in the upcoming lectures, but I just wanted you to have a fairly good intuitive understanding of that from this lecture itself. Now we can visualize as a scatter plot these two data sets, right? So scatter plot we have covered in detail in the last lecture, so we have to use plots, using plots, and scatter of data 2.x comma data 2.y. I'm not going to plot the axis or anything, I just want to see the data plotted as a scatter plot. So here we should have two straight lines. Yeah, so one set of data. In fact here what are we plotting? We are plotting, we are plotting x against y only. So x axis, we don't have two sets of straight lines. We are simply plotting how x relates with y. When x is 1, y is 6, x is 2, y is 7. So there is a linear correlation between x and y. However, linear positive correlation. However, if it was something like this, 10, 9, 8, 7, 6, that means when x is increasing, y is decreasing. So the data should be, after running this, it should be like this. So this is scatter, and if we type plot, this should be a straight line inclined like this. So there is negative correlation between x and y. As x increases, y decreases. So that visualization basically gives you that idea of the relationship between two sets of variables. Now we can stop with one simple activity. Here is a numerical example. I have defined a data set here, temperature as a function of sales. It can be something like when salespeople who are supposed to travel and make sales, maybe when the temperature in a day is very high, the number of sales that they make is less. You can interpret this in whatever way. Now what we are asked is to calculate mean, median, mode, variance, standard deviation, correlation and covariance. Basically all the 7 parameters, statistical parameters that we discussed in today's lecture. So fairly easy, right? So let's calculate the mean of both. Actually we have to calculate the mean of temperature and mean of sales. So let's do, I don't want to store this in any variable, so I'm just simply going to do mean of activity data dot temperature, that is 31.6. so this is the mean value. Then mean of sales, 108. So the number of sales, or this can be sales amount or volume of sales, whatever it is, it's 108. Mean temperature is 31.6 degrees Celsius, I assume. Then standard deviation, actually mode, let's calculate. Mode will be exactly the same, except now the function we need to change to mode, and mode of temperature and mode of sales. So here I will print it in two different lines. So print ln and print ln. So 30 and 100, that is the mode, because 30 and 100, simply because there are no repeating numbers, so mode will be the middle value, I guess. 25, 30, 35, yeah. So this is mode is 30 because it's the middle number, and 108 100 is also the middle number, so 80, 90, 100. So median will also be the same thing. Now when we calculate median, it will be same as mode. Okay, fine. Now let's calculate standard deviation. So STD, this is standard deviation, variance is VAR, and we need standard deviation of both temperature and sales. Temperature has a standard deviation of close to 6, sales has close to 27. Variance will be a very high number because its order of magnitude is square as that of standard deviation, right? So obviously it's a big number. And now let's come to the interesting part, which is covariance between temperature and sales. So, and then let's also calculate correlation between temperature and sales, COR. So the covariance between temperature and sales is 164 and correlation is 0.99. So what this says is, as temperature increases, sales increase. Okay, maybe I don't know how it makes sense, but that is what data is telling us. And if we were to plot the same thing, plot instead of data2.x and data2.y, we will be plotting activity data.temperature on the x-axis and activity data.sales on the y-axis. You see there is almost like, and we can plot this as a scatter plot actually. It's almost a positive correlation, 1-to-1 correlation. I don't know why plot was showing a weird, I'm not sure. Okay, because of the order of the data. Okay, so scatter plot is better in this case. You can see that the higher the temperature, the higher the sales activity. It's what the data is telling us, but here we can calculate all the parameters, and we know that somehow temperature is positively correlated with sales. Maybe this temperature you can imagine to be temperature in Fahrenheit, then it makes sense because 30, 25 are all extremely cold temperatures, whereas when temperature increases, people can travel more. Maybe so. If this is Celsius, then it does not make sense, but if this is Fahrenheit, of course it makes sense. So I hope this gives you a fairly good idea about the basics of statistics, which I'm sure already you would be knowing, but the implementation of that in Julia. And I want to take a moment to appreciate you for finishing up until this point in the course. And now we are officially wrapping up the data science part of the course, and I know that we are yet to start implementing actual neural networks, which are probably an integral part of many data science projects, but we'll be entering into that in the next 2 modules. So the next entire module will be machine learning in Julia, in which we will be covering many conventional ML models, and the module after that will be deep learning in Julia. So the most exciting part of the course is beginning from the next lecture onwards, and I know that you have been waiting for that throughout this course, but I really appreciate you for reaching till this point. Now your foundations are very strong, you are very comfortable. If you have followed through the lectures and if you have implemented all the code by hand, now you are very comfortable using Julia, you are very comfortable running it every single time, you are comfortable installing packages or importing them, you are comfortable thinking about basic mathematical operations performed in Julia, you are comfortable dealing with arrays or basic vector operations, etc. So let's get on to more exciting parts of the actual machine learning model building from next lecture onwards. So take care and see you then. Bye.